thank you for joining us. It's lovely to have you here.
Thank you. It's wonderful finally being back to PI after this long absence.
Well, thank you for coming. And I was struggling with ways to introduce you to our audience because there's so many things that theoretical physicist and author and world traveler and philosopher. So I decided I didn't want to introduce you. I want you to tell me, pretend I'm a stranger on a plane and I just sat down next to you and I buckled up and I say, "Hey, what do you do for a living?"
That's a bad way. I would say, hi, my name is Carlo. I was born in Italy and I go around and talk with people. I have ideas. I try to do them. What about you?
I talk to people like you trying to figure out what they do. So it's a good thing we're sat next to each other on this plane. You didn't mention theoretical physics. Is that because what you consider yourself doing is more just talking to people about a variety of subjects?
No, it's if you have to define me what I am, primarily I'm definitely a theoretical physicist. The rest of the things that I do are in part motivating, part around that. So my competence, if I have any, it's in theoretical physics. I don't like to define myself, even in front of myself. So I like to keep, things open. And when I started writing books for the large public, there was a moment in which I was telling myself, "Wait a moment, are you just turning into a writer instead of a scientist?" And then I realized that this is a meaningless question. I'm just doing what I'm doing, and things are connected. The only meaningful question is how many hours I devote for one and the other. That's maybe a question.
Well, I ask partly because you're currently you have a position in London, Ontario, at the Rotman School of Philosophy, which seems, at least on the surface, to be a strange place for a theoretical physicist to be. Can you explain what you're doing at a school of philosophy?
I talk with philosophers. I love to talk with philosophers because I think it's useful for physics. I have this conviction since a long time. I was interested in philosophy since I've been interested in philosophy since I was a kid. I guess when I was a student studying physics, I also continued to studying philosophy. And I think that the clear-cut separation is a bit artificial and is damaging for both disciplines.
How so?
Well, first of all, of course, not all physics needs to talk with philosophy. In fact, most of physics does not need to talk with philosophy. If you have to, solve the Maxwell equations for a certain antenna, you just might happily ignore philosophers for that particular problem. And a lot of physics is just concrete, specific problems.
Right.
But of course, there's a part of physics which is not to apply knowledge that we have for solving problems, is to find out what is the knowledge we have at the basis. And that part, it's a kind of things that, Einstein, Maxwell, or Newton, or Galileo, Boltzmann were doing, or Heisenberg. And that kind of activity traditionally was done by people who were schooled in philosophy. I mean, Einstein had deep knowledge of philosophy, and so Heisenberg and certainly Newton, Galileo, he was avid reader of Aristotle. Because there's a mistake in the understanding of physics and science in general. Science is just collecting data and writing equations that predict this data. I mean, that's just a little part of it. The largest part of it is figuring out a set of concept, a conceptual structure, how to think about that. When you go from, the Ptolemaic to the Copernican system, you don't just collect data and make, you rearrange the order of the world in a different way. And you do the same that's what Einstein did, that's what Maxwell and Faraday did, that's what Heisenberg did, and Boltzmann and so on. So the core problems in fundamental physics today, like quantum gravity, the problem in which I am, do require the same kind of rethinking the conceptual basis of a discipline. And the philosophers are very good in that. Not because they solve the problem of physics. I mean, relativity was found by Einstein, who was a physicist, not a philosopher. But he's a physicist who was listening to what the philosophers were saying. Philosophy has a capacity of critical thinking, which is very deep, has imagination. Philosophers come out with completely different ways of thinking about reality. Sometimes crazy, we don't care about them, but that's not the point. Sometimes very useful.
Sometimes I think the theoretical physicists come up with ideas of reality that strike me as crazy too. And
sometimes they do, sometimes even perhaps too much crazy. And you should listen to philosophers who say, wait, come on, don't exaggerate, guys.
Are there certain open questions in physics that you think would most benefit from input from philosophers?
Yes, and they change, of course, because physics is a process, and right now the number of open questions where philosophical thinking, philosophical clarity is useful. Some of them, for instance, have to do with time. Uh, uh, in trying to write a quantum theory of gravity, of course, space and time have to change, because now we're looking at the quantum property of space and time. And we have so many prejudices about how space should be, and how time should be. And a careful philosophical analysis of what we know, I find it useful. That's one of the things I'm exchanging with philosophers I'm in touch with. Even in simple things, one very well known problem about time is that the past is different from the future. And so, what's the root of this difference between past and future? Is that something intrinsic in time by itself or not? And the answer is not just academic. Well, yeah, it is academic, but the question is important, because if we want to understand more, to understand how quantum gravity works, we have to get clarity about these things. So the nature of time is it's one. The nature of observer is another one. We now are in this funny situation with quantum mechanics, which is a fantastically good theory, but it's formulated in terms of an observer. So why do we need a guy with a PhD in physics to formulate, to understand how the things work? No, I mean, things work by themselves without an observer. So how to make sense of that? And these are questions that physicists have been struggling with, and they will come out with a solution. I think solutions are being debated around the table. But philosopher can listen, contribute, and provide perspective.
I was struck when I have your book here, Reality is Not What It Seems, about quantum gravity, and we'll get more into quantum gravity. But what struck me most was the book essentially begins with the ancient Greeks. Quantum gravity and loop quantum gravity are relatively new fields of physics, but to explain them, you went back thousands of years. Can you tell us what inspired you to go so far back to bring us to the present of quantum gravity?
That book, Reality is Not What It Seems. It's actually the first popular book that I wrote about science, and I wrote it quite late, after so many people had told me, "Why don't you write a popular book about quantum gravity?" It was at least 20 years that people were telling me that and pushing, and some publishers also. Like, come on, Carlo, you write nice. Why don't you write you have this beautiful science. Why don't you write about that? Also because people were sick and tired with string theory. I mean, just can't stand string theory anymore. So let's do some good quantum gravity. But I didn't know how to do it, because how do you tell quantum gravity to people, right? I mean, you have to digest general relativity, you have to digest quantum mechanics. It's a long story. So for long I hesitated, because I wanted to do physics and not waste time writing. Then I started considering the idea, but I couldn't find the right way.
Mm-hmm.
And then it was a flash. I had so many things to do, but I couldn't organize them. And I mentioned in one of the preface of my books, and I don't remember which edition, I was driving from Italy to France, where I had moved at the time, and in the middle of the night. And then I said, well, I need to explain this concept. I need to explain this concept. I need to explain this concept. I need to tell the reader what is a field.
Mm-hmm.
Is electric field. It's not clear. I need to tell the reader what exactly we mean by geometry. It's not what we use. It's subtle. I need to tell a reader that particles are not precisely particles, so there's some discreteness, some granularity.
Mm-hmm.
And then I started thinking, where maybe I should say when these ideas were born. So the ideas needed to understand. If I tell how they're born, and suddenly the entire history, the narration came in front of my mind. I said, of course, I just talk about Democritus.
Right.
I talk about Galileo. I talk about Faraday. I talk about Maxwell. What problem they were addressing, how they come out with that particular solution, and why we're using this notion now, and how this notion built up, changed, and came all the way to quantum gravity. And that is evolution of the world. At the time of Descartes, in the Renaissance, there's this idea that this is res extensa. Then Newton comes and says, okay, I got the world. It's a space, time passes, and there are some little stones that move around with forces. That's how. And then Faraday comes, and wait, you're missing something. There's a field. Okay, and Maxwell put order in the field. And then Einstein comes and said, look, the space and the time are actually mixed. So you should not have two different things. You should think to talk with another.
Space-time.
Space-time. And then Einstein, 10 years later, realized that the space-time is a field. Wow. Okay, now we connect the notion of field with space-time. And quantum mechanics connect the notion of a particle with a field. So unless you go through the way these things developed, you don't get them, I think.
Yeah.
So I decided to write a book without details, but with a core flow of ideas. That's how it came out.
And when that epiphany hit you while driving, I know what happened after that.
You know what happened after that? I got a ticket.
Because you were driving too fast?
I was driving too fast. It was an empty in the night highway. I was so excited.
You had the pedal to the metal?
The first chapter is going to be seen. And then somebody I hear, wow, shit. And I look at the speedometer, I don't know how you call it in English. And I'm going, 180 kilometers per hour on the highways. Oh, no. So I had to pull on a side, and the policeman said, "What the hell are you doing?" And I was, I just told him. I said, "I'm sorry. I just was going extremely fast." The reality was I was not even in a hurry. I just got an idea how to write a book, and was so happy with that. I just was excited. And the policeman said, "Okay, good luck with your book," and let me go.
He let you go.
Yeah.
I'm dying to use that excuse someday. Oh, no, I was speeding because I figured out how to write a book about quantum gravity. I don't think it will work for me, but I'm glad it worked for you.
Yeah, it's good to know that works. I have a question. A lot of what you're talking about, it seems that it's very fundamental, this idea of unlearning things, both when you're writing books to encourage your readers to unlearn some things, or even in your research. I think that when we're thinking about something, we can be stuck in certain ways of conceptual thinking, or be making some assumptions and not even realize it. Are there certain strategies that you've learned, perhaps from philosophers, that encourage you to challenge your conceptual ways of thinking?
Oh, that's a very good question. I don't know the answer. The premise of your question are, I think, the most fundamental point about learning. The difficulty of learning is not to learn something new. That's easy. The difficulty of learning is to unlearn what we think we know. We're all deeply convinced that we're right about the way we see the world. Everybody, including myself. And so we just don't give up easily the ideas we have. And we don't learn unless we give up.
You wrote once that science is born from an act of humility. Is that do you mean by humility the idea that we can accept that we don't know everything?
That, but even stronger, the idea that what we think we know, we might be wrong. And so what we don't know is so much more and so large that we shouldn't rely so much on what we know. Yeah, I think humility, there is this beautiful letter by Newton. Newton was arrogant, pretentious, perfectly aware that he was the greatest thinker of his time. And 3 centuries later, we still think he's a greater thinker, maybe in science of all the times. He was aware of that. And at the end of his life, he writes this letter. He says, "I don't know how the others are looking at me or will be looking at me, but I myself look at myself like a kid playing with little pebbles on the shore in front of the ocean of our ignorance. That's why he succeeded in being Newton, I think, because he was perfectly aware that there was everything to be discovered. And
so he was both arrogant and humble at the same time. Arrogant
exactly.
about his
Arrogant
skills,
and
but
humble. It's
humble
the mixture of the two. You can be arrogant with respect to the others, humble with respect to your ignorance, and the fact that that we might be right, we might be wrong. I've been reading this summer because we're doing an audiobook in English, Galileo greatest book. It's the dialogue of the two maximum systems of the world. It's a fantastic book. It's a book that convinced humankind, in fact, that the Earth is moving. It's spinning and it's going around the sun, and it has all the argument for the Earth to move. But reading it, surprise is that the arguments are just a few pages. The large part of the book is to convince the reader that it's possible to question what he give for granted. It's all about, look, you think that, but that might not be right, and give an example, given thing. It's only when 3/4 into the book, say, okay, now you're open to the book. I haven't argued anything. I've just told you, consider the alternatives. Only at that point, he brings argument for the movement of the Earth, which, by the way, are wrong argument. I'm mistaken. We know that. But nevertheless, he convinced the world not by giving good argument, in fact, there isn't wrong, but by showing that there's nothing wrong in accepting that something completely obvious to you is it's not right. But that was not your question. Your question, well, what's a strategy we can go into for not being trapped in our own beliefs? And I don't know. I think it's because we are, and scientists are like everybody else,
right?
And it's more than being aware of that, keep repeating to ourselves that I don't know what's the right way of doing so.
Do you remember a moment in your earlier life when maybe physics or science itself sort of revealed to you this this new way of looking or unlearning things you may have known, open your eyes to new possibilities? Was there a sort of a epiphany there, or was it a series of happenings?
It was a series of happening starting from when I was a student. I fell in love with science late, when I was already a university student in physics, and in studying modern physics, it was a series of shocks. Like, oh my God, somehow reality is not what it seems. That became the title of my book. So it was a strong experience at that time.
Is that a phrase that you've had in your mind for a long time before the book came out, that reality is not what it seems? Was that sort of the realization you had those years ago?
The concept, yes, for sure. Somehow it grew with me in various manners. The phrase itself, I'm not sure. I think it came from the text of the book, and then I picked it up because I think it represented what was going on.
We were talking about, you mentioned quantum gravity before, and there's a line in your book, 7 Brief Lessons on Physics. It's just such a simple, short line. There is a paradox at the heart of our understanding of the physical world. And that paradox is essentially, I think, the root of quantum gravity, the paradox between general relativity and quantum mechanics. Can you elaborate a bit more on why that's a paradox? What paradox we're struggling with and why we need a solution to
it? Yes. I believe it is an apparent paradox, but it's a strikingly paradoxical the way it looks. And I think the way I describe it in that book, I'm not sure it's that book, is it's what a student of physics learns when he goes to school at the university, and he just minimally think. Because you go to classes on quantum mechanics, and you get to explanation of the world, and the world is all about discreteness. Think, the light is photons, and it's just discrete particles. The elementary particle bits of things. Everything is in bits and chunks. It's probabilistic. Things jump from one to another. And there is this strange interactive thing for which in quantum mechanics you predict how things interact with one another. So you say, okay, that's the way reality is. I mean, okay, God did reality that. I mean, we don't know what she thinks or why, but that's where reality. And then you go to the other class, or this other teacher that teaches you about general relativity. And this is, equally immense, fundamental, successful theory. And the universe is continuous, it's perfectly continuous. There's nothing probabilistic. There is, deterministic equations of motion. Everything is perfectly objective out there. You can write the history of space-time in a single equation. And then I think, wait a minute. I mean, either one or the other, they cannot be. I mean, my teachers stopped talking to one another, haven't talked to one another for 30 years. And they're both professors of physics with a PhD and tenure. So it's really two totally different images of how reality works. And, God can be complicated, I don't know, but not so self-contradictory. The world is either this way or the other way, or some way which is compatible with both. But what is the one that is compatible with both?
And is that the quest
that's
with quantum gravity?
And
Exactly.
speaking of quantum gravity, as part of this show, we collect questions from other listeners. And a mutual friend of ours, Carlo Lynching Chen, she's a postdoctoral researcher in Brussels, Belgium. She sent in a question for you.
Oh, fantastic.
Hi, Carlo. This is Lin Qing. So, in our quest for a theory of quantum gravity, do you think we will need new fundamental principles that both quantum mechanics or general relativity have not yet revealed to us? And what is your strategy for finding them out? Thank you.
That's a great question. She's fantastic. And it follows immediately from what you were asking before. The answer I have, I'm not sure, but that the answer on which I'm working is no. No to the question, do you think there is some fundamental principle that will be missing? And I think that the idea that, we're missing something crucial, fundamental down there is just wrong. The point is that we have to take seriously what we learn with quantum mechanics and seriously what we learn about general relativity and bring them together. And they do go together. You just have to rearrange things and to understand that. So I'm a very conservative guy from this perspective. I don't believe we need something new. Supersymmetry, other worlds, many dimension, breaking of Lorentz invariance, correction to quantum mechanics. Nature has been saying no to all the attempt to test this alternative hypothesis so far. So I don't see any evidence that we're missing something. It's just that general relativity, it's about space-time. So it's the shape of space-time, shape of space and the shape of time, which means how different clocks move with respect to one another and how meters measure geometry. And that's quantum. And so we have to understand the quantum properties of time and the quantum property of space. And, that's radical. So the assumption is conservative, but if you follow up, this is completely radical because it means it's a continuous space that you thought was, forget about it. The time evolution in a single variable, forget about it. You have to replace the usual way of thinking space, the usual way of thinking time with something consistent with quantum mechanics, but not the quantum mechanics in space-time, quantum mechanics of space-time. So for instance, you have to have a mathematics and a physical intuition that allows you for having quantum superposition of space-times, plural, of geometries. Like there is a Schrödinger cat that can be both awake and sleep, or somebody said dead and alive, and alive, but I don't like
I
that.
like your version better. I like cats. So.
Yeah, exactly. So Schrödinger cat in quantum mechanics can be both awake and sleepy, and sleeping. And so in the same sense, space can have a shape and also another shape in a superposition of the two. And of course, this requires imagination, finding the right concept to talk about that. That's also where philosophy comes in useful, and the right mathematics. And I think loop quantum gravity is an example of a theory that attempts to do that. We don't know if it is right. It's very conservative, and that's why the answer to Lich's question is no. So there's no other principle to be added, but it's completely radical then because it forces us to rethink the basic notions.
You mentioned evidence when you were giving this explanation, looking for evidence to support various theories of quantum gravity. What kind of evidence would you be looking for?
I think that recently there have been a lot of evidence that helps us. And in science, evidence is never definitive, it's always indications, like in life, by the way. So it's not that you kill theory. It's very rarely that you really, really kill a theory with an experiment. But you create problems to a theory. And when theory have too many problems, you look somewhere else. And there have been a lot of these things recently. The strongest and the most unexpected for many people has been the absence of low energy supersymmetry. There was a big part of the community that was completely convinced, sort of 99.9%, that supersymmetry was going to be detected
by the Large Hadron Collider?
At CERN, right, with LHC, and it wasn't. It was a shock. There was title of the journals like, this is a crisis of physics. Of course, it's not the crisis of physics. It's only the crisis for those who expected it,
right? Which
is not physics. It's just a particular school of thought. But that's nature talking. And when nature talking, we should listen, I think. Another example, it's breaking the law of Lorentz invariance, the symmetry at the basis of Einstein's special relativity's Lorentz invariance. Some people thought this was very good. Also, that was like supersymmetry. It was a very good, very nice idea. You can make the problem of quantum gravity easier if you don't have a Lorentz invariance. So people try to write theories which break Lorentz invariance and might be quantum gravity theories. So this was tested 10 years of, 15 years now of astrophysical observations, and all the expected signs of breaking Lorentz invariance, 0. So once again, nature talks. As far as we know, nature is saying, no, guys, that's not the right way to look for the solution. So I think nature is giving indication. I mean, a lot of people expect a negative cosmological constant. Even today, there is a large part of the community that continues to do calculations with a negative cosmological constant. It's called ADS-CFT. ADS means anti-de Sister, which means it's a space with an effective negative cosmological constant. Except that the cosmological constant has been measured by the astronomers, by the cosmologists in a very convincing way. They got the Nobel Prize, the ones who did that, and it's positive. So once again, I think my interpretation, my reading of that as a scientist, I might be wrong. I know I might be wrong. But my reading of that is that nature is talking, listen, that's not the right direction to go.
So what will nature say to you? How will nature speak to you to advance loop quantum gravity, say? What signs are you looking for?
There are 2 or 3 directions where me and many of my colleagues are looking into. For the moment, 0. So we have no negative response for nature, but we don't have any positive response for nature.
Can you explain that a bit?
We don't know. So there's nothing that has come as a sort of contradiction to what we expected, but there is nothing that has come to confirm predictions of the theory either. So I cannot say that quantum gravity is confirmed in any sense. It's a tentative theory. It's just out on the table, and let's see. So where could the confirmation could come from? I see 3 possible directions. One is early cosmology. There's a lot of literature, papers written. So the universe, we know, came out from the Big Bang. The very early moment at the beginning of its life was deep into quantum gravity regime. So that's where quantum gravity should play a role. And a lot of colleagues have applied loop quantum gravity to describe what happens there. It seems to be working, and to see if one can predict effects of what happened there that can be tested in the cosmic background radiation. It's possible. People are working, measurements are getting more precise. I hope they will converge to something useful, but for the moment there is nothing. That's one. The second one is black holes. I'm working on black holes. Loop quantum gravity is consistent very much with the idea that a black hole evaporates. That's Hawking great realization. Black holes evaporate. They become smaller, smaller, smaller. And then at the end, they don't just disappear, pop out of existence, but there's a remnant, which is a white hole. So there's a quantum gravity transition, a jump, famous jump of quantum mechanics, from a black hole to a white hole, with a little throat but a huge inside. And then this white hole slowly, the things come out, so the information slowly come out, lives for a very long time. And this is a scenario, it's a possibility. It might have astrophysical consequences. These are being explored, various groups, including in London, the people I'm working with. Is one of this possibility which I'm particularly attracted to, which is that these little things that float around in the universe, these black hole remnants, which are white holes, are actually dark matter. That's what, or a component of dark matter. If so, it might be that we've already observed something. We just haven't recognized it.
Right.
Okay.
Dark matter being another great puzzle of modern
dark
physics.
matter it's a big puzzle, and that's the opposite of the quantum gravity puzzle, because it's not a puzzle in our understanding. It's a puzzle in what we see. So we see, you look at the universe around us, and we see galaxies, stars, clouds of hydrogen, all sorts of stuff. And then there is this stuff out there. We're not even sure it's stuff. I mean, there is something that produces effect out there. We see the gravitational effect of these things. And we have quite convincing evidence that it's not usual matter. It's not just atoms or molecules or protons or neutrinos or photons. It's something else. And it's a lot. It's quite as much normal matter and dark matter, even more dark matter than. And nobody knows what it is. So it's fantastic. It's people who say that we're close to the end of physics and close to the theory of everything. Come on, guys. We don't even know what we see around us. So dark matter is really an open question. We have a lot of possible explanations, but too many and non-confirmed, non-really credible. I like the black hole ones because it does not rely on any new assumption. You can say, oh, dark matter is some new kind of particle we haven't seen yet. While if it is black holes, it's just general relativity and quantum mechanics.
Right.
So something we know exists. But I don't know. It's an open question.
It's funny you said it's a mystery, we don't know, and that's fantastic. And that that's not always the case in a lot of professions where the lack of knowledge about something is something you're excited about. Are you glad that physics is nowhere near being complete?
Oh, infinitely so, of course. Of course. Yeah, otherwise it would be boring, right? If we imagine what a disaster if we got somebody wrote, okay, I got it, everything, this is the final equation of everything.
But that's what you're going for.
No.
No?
No, zero.
Is quantum gravity not sort of that grand unifying theory?
No, it's a step on the way.
Okay.
It's just figuring out what are the quantum properties of space and time. I mean, then there's so much more to figure out. I'm not working for a theory of everything. I'm working just for a next step in understanding what's around.
So what would be beyond quantum gravity in our understanding, or once we've figured out the quantum nature of space-time, does that open up new questions or help us answer old ones?
You're referring to fundamental physics, right? Because of course there are plenty of questions which are not fundamental physics, like what is consciousness, or how a thunderstorm really works, which haven't been figured out yet. But in fundamental physics, suppose loop quantum gravity is confirmed, okay? I with a colleague, Marius Christodoulou, we have an experiment which we proposed, which might even be doable in 10 years or so, which would actually test the discreteness of time predicted by loop quantum gravity. So suppose this can be done, okay? And bingo, the right numbers because loop quantum gravity predicts that space is discrete, right? It's granular, nothing continuous, it's really granular. Like light is made by photons, space is made this grain of space, but also time I expect it has this granularity. And we have an idea of perhaps with some slight advance in technology, not excessive, could be tested. Now, suppose this come out right, okay? Bingo. Loop quantum gravity is correct. Perfect. The right numbers are there. Now what? Well, now we still have a universe described by a funny standard model where the weak interaction and the strong interactions are completely separated, described by similar theories, but not really unified in any way. Gravity described by still another theory. 19 parameters of the standard model, with who chose them, why 3 generations, why? We have, suppose with quantum gravity, we figure out the Big Bang. And what seems likely is that it was not the initial explosion, was a bounce. It's an idea, not just in loop quantum gravity, idea studied by various people.
That our universe is the result of a previous one collapsing
so there
and
was
expanding again?
some universe that was collapsing in some sense under its own weight. It gets to the sort of maximal compression where quantum gravity comes in, it bounces, and what we see as a Big Bang is this bounce. I think it's a reasonable hypothesis. It seems to be more reasonable than the Big Bang, but we don't know. Suppose we figure this out. Have we solved everything? No, of course. I mean, what was the collapsing universe coming from? I mean, what was there?
Yeah.
I mean, it's all open. It seems today so impossibly difficult to figure out what was in the collapsing universe. But, at the time of my grandfather, it seemed impossible to discover what was the chemical composition of Jupiter.
Yeah.
I mean, it was considered unsolvable problem. I mean, now we know in Jupiter everything. Even, there were ants there, we would have seen there. So science finds new problems and grows at all levels. And know if there are mysteries is not a reason of sadness, it's a reason of joy because there are new things to discover. It's a beauty of understanding.
You're still like Isaac Newton playing with pebbles on the vast sea of what we don't know?
Absolutely.
Yeah.
And regarding this, general idea of working in a field where you maybe don't yet have evidence for or against it, it just reminds me of something you write about in your book, The 7 Brief Lessons. When you're talking about Einstein's theory, you write about how a lot of times something very important is kind of considered useless at the time when it's developed. One example you gave is that Riemann's work that was generalizing Gauss's explanations was considered useless at the time, but it was then a fundamental piece of Einstein's theory. So it seems that this is very crucial to work on things where we don't actually know exactly what the application will be or exactly how long it will be. But I'm wondering if you think that physicists need to find in general some kind of a balance between working on problems where we have an idea of the time horizon for the applications versus working on these problems where we don't really know where it will lead.
Yes, obviously there is a balance to be searched there. I think if you look at this from the main whole of perimeter institute, it seems hard to find balance. But if you look at it on a large scale, 99.9% of the money put into research worldwide is to practical applications. And the tendency is to go more toward practical application. And that's a disaster, I think, because of course we need practical application, right? We need people who study chemistry of material because we need a certain material for something, for healing people and replacing bones. I'm just defending. So applied science is great, but to concentrate resources toward applied science so much as is done today, I think it's a disaster. We need people who do the kind of pure science or fundamental science or basic science. I mean, all these words are imprecise, all of them. Namely, don't think about application. Just forget applications. because somehow our science is built upon a number of key results obtained through the centuries. If you look at each of one, no one was looking for application, and if he had looked for application at his own time, he wouldn't have got there.
Mm-hmm.
So it's obvious that we need to just ask the question: what's behind things? How can I understand better at the fundamental level? Applications will come out, sometimes fortunately, sometimes unfortunately, because sometimes applications are to kill people and to make war. And let's not go into that.
Mm-hmm.
So you're the organizer of a research initiative called the Quantum Information Structure of Spacetime, and this brings together theorists, experimentalists, and philosophers. Can you tell us why you think it's so useful to bring together that group of people and what you're trying to answer through this initiative?
Yeah, thank you for this question. Quantum Information Structure Spacetime, the short name is KISS. KISS written with a Q, but we like KISS. It's a big consortium with big grant, mostly used for supporting young people, postdocs. A group of PI here, in fact, 2 groups of PIs are part of it. And there are about dozens of groups all over the world, from Hong Kong to Mexico to California. And the aim is to bring together 2 communities, or actually 3 communities. The 2 communities are quantum information and quantum gravity. And the idea is that quantum gravity people have been using quantum information notions, or beginning to use in various ways. And quantum information people are starting thinking about how quantum information works in space and time, let me say it this way. And so the same problems are being addressed from a completely different perspective. And the third community is philosophers, because this dialogue opens fundamental questions, like what we were saying before, the direction of time, or the nature of what is information, what we mean by information. And in quantum gravity, it's a theory which is not written in space-time. So in some sense, space-time have to be rethought to come out from the theory in some way. And these are philosophical questions. So these are different communities which are being brought together. And in June this year, there will be, not far from PI, in London, Ontario, so it's just a short drive from PI, a conference bringing together this. And it's a conference that we have organized. It's not a standard conference with speeches and a few questions. I mean, why do you say that? Each half day will have a few 10-15 minutes of very short flash presentations, and then a couple of hours of open discussion, everybody with everybody, in which the different opinion are being with a good chair who sort of tries to balance and follow. So discussion, comparison, point of view, because there are these communities, quantum information, quantum gravity, and philosophers who look at these things, which have different ways of viewing the same thing. So we want to compare and of course, learn from these differences.
Are there frustrations that tend to come up when people with such different backgrounds and education are trying to discuss a topic with each other?
Yeah, absolutely. Because there are things you give for granted. Then the person who's a good scientist come to you and say you're wrong. Say, wait, you're wrong. You're wrong, and that's frustrating. And then, but that's great, because I think that's how the process of knowledge works. And we learn from experiments, but we even more learn from continuous exchange of perspective. And the more we listen to other perspective, and that's a great opportunity, I think, because quantum information has boomed for various reasons in the last decade, probably. And there are very good ideas there, which I think are relevant for quantum gravity. On the other hand, the people of quantum information are not aware that some of the things that they are struggling with have already been addressed by quantum gravity, right? So there's really a dialogue to start here. and the philosopher are interested in both and have things to say about both. So I hope that this dialogue in 3, based not just in presentation but in discussion, will work, and I look forward to that.
Mm-hmm.
I'm sorry. After 2 years of lockdown, of pandemics, and people staying at home, how have you felt distinctly the absence of in-person gatherings with other researchers and scientists, getting together in the same place?
A little bit, yes. It has, for me, it has not been dramatic because we're all on the internet, we're not on Zoom, but being always on Zoom is also painful. And this morning, finally, it's the first day I'm back in PI. So long. Finally, I was with a young colleague, Flaminia Giacomini, in front of a blackboard, writing things. I say, no, wait, it's not this, it's not that. Oh, what a pleasure. It was so long this didn't happen.
Beautiful.
And from reading the website for this KISS initiative, it seems that a major goal is to deepen the understanding of information. Could you just tell us what you think of information as meaning and why you think that information is so fundamental?
Yes, information is a very tricky word because the spectrum of meanings is very wide, extremely wide. So it's also, when talking about information, people often get confused because in a debate, in a dialogue, people mean different things. And you go from the most complex one. I mean, you have information about your father. Of course, I know a lot about my father. Right? To the most basic one, which is my little card here contains so many megabytes of information. Okay, obviously the two are connected somehow, but the two are very different, completely different. About your father is something that has to do with meaning. In that case, with rather even emotions, but certainly it's interpreted information in some sense. So it has to do something that needs to be decoded, that can be translated. While in the case of the memory card, just counting something is a number of counting things. I counted the number of atoms, or counting the number of something. In this spectrum, I think that what is interesting is exactly the spectrum that has so many possible meanings. But what the most interesting is the basic one. And the basic one, there's a very simple notion of information which is purely physical, which is correlation. When two things know about one another. If you glue two things, if one point one direction, the other also point in that direction. So if you have information about one, if you know one, you know the other one. So one has information about that, meaning that there is a correlation between the two. That's a basic notion of information. It's purely physical, nothing mental, nothing, no meaning, no significance, no. That's a basic notion of information. And I think this notion of information is fundamental. Not because the world is made by information. The world is made by stuff, by variable, by things which are. But because the world is made by relations. The properties of things are relative to something else. So if you want to describe the structural world, you're always talking about how one thing affects another one, so how they get correlated to the other one. So immediately you can quantify how much things affect one another by using the notion of information. And this means not that information is an ingredient of the world, but it's a key ingredient of our thinking about the world, our thinking about the variables. And I think quantum mechanics itself can be largely thought in this way. I've been thinking this since back in the 90s when I started thinking about the notion of quantum mechanics. And because of that, I think in quantum gravity also it could be a fundamental role to thinking about information systems have about one another. But once we go into this way of thinking about physics, not as how systems are, but how systems have information about one another, how they're correlated, then it's easier to understand that there's a continuity to the most complicated notion of information, the one about your grandfather or your father, right? So the mental is not so far away from the physical now, because we start taking the physical from the right perspective, from which is easier to reconstruct the more complicated notion of information. Meaning, for instance, we talk about memory traces, and we build up more and more complicated. So it's a very versatile, rich, confusing, but key notion for understanding the world information, because the world is made by relations, not by things.
Mm-hmm.
In reality is not what it seems. There's a passage that I loved. I even told you about it after I read it, because you go through so much of the book explaining the historical context of quantum gravity and explaining the concepts in very easy to follow terms, which I appreciate. And then late in the book, you say, if, dear reader, you have found the journey so far a little rough, hold on tighter, because we're now flying between voids of air. And then you get into your new ideas, which you said, if the ideas seem confused, it's because the person with the confused mind is me, yourself. That's, first of all, that's something I don't often see in popular science books, is the warning to the reader, like, it's okay to be shaken by this. It's okay to not fully get it. So you gave this warning, and then you expressed ideas that you personally don't have a full concept of. Can you explain a little bit about what that's like, going into territory that is less historically sound and more speculative, and putting your own ideas out on the line like that?
Yeah, I think that there is a lot about the world that is we understand, and there's a lot we don't understand, and it doesn't make much sense to do what we too often do, in my opinion, which is to pretend that we understand the part we don't understand.
Mm-hmm.
Maybe it's just my education or my way. I mean, it's certainly university professors that teach lecture in physics. They shouldn't pretend that they know everything about it. They don't know about it. And they may be wrong. I mean, they will be teaching things which are wrong. So they should say, look, this is what we understand. This is what I understand. And be aware that there's be something wrong. And if there's something confusing, it might well be because it is confusing.
Mm-hmm.
And it might well because the person is confused, or because the community is confused. A good example is quantum mechanics. Quantum mechanics is 100 years old, spectacularly successful, used in technological applications everywhere, but it's still confusing. And the fact it's confusing may be good, because it may be that we still haven't got some right way of looking at it. So let's say it's confusing, not hide it. And I think this makes also things easier for the student at the university, or for the reader of a book, who is not presented this, smooth, white, clean piece of stone. Say, this is it, period.
Mm-hmm.
No, I mean, we are humans. Science is a human activity like everything else. It's dirty, it's imprecise, there are holes. So I think it's better to present what it is.
I think I connected with the idea that you yourself are struggling with these ideas. And, when you read a book by an expert on any subject, you assume the expert knows everything. And for you to say later in the book, here's what I'm grappling with, it helps. I think it helps the reader understand that this is a difficult, complex pursuit.
Yeah, my books are a little bit different in spirit from most popular science books, because they also are aimed as a slightly different audience. And in fact, I've remarked from the reactions that I get that the typical reader of science book likes my books less. And the people who like my book are at both the two extreme sides. Are either people who know zero about science, or people who know a lot about science.
Mm-hmm.
And I understand the reason, because I think at these two extreme categories when I'm talking about. Somehow, what I do, the typical science book, it's written for somebody who want to know more and more and more and more and more about some domain.
Mm-hmm.
Okay. So you give more details, you give more information. Say, oh, and we know that, and we know that, and we know that, and we know that. And, there are kids, nerds that really want to know more and more and more about the neutrinos and all the possible details about that. I don't do that. Zero. I do the opposite. I take away. I strip away as much as possible, trying to reduce to what seems to be the core that we have understood about something, and to present it in a way that it stays together. It holds on and allows the reader to understand what it is and what seems to me the real thing we have understood. And then, of course, those who know nothing about science, they like it because they say, oh, great, I get to the idea. And those who know a lot about science also like it because they say, oh, wow, that's a good way of viewing things. Maybe I didn't think this way. Maybe I was thinking the other way. That's a new perspective on things. And a lot of my best colleagues tell me, I read your book. Wow, I didn't think about this way of putting it. Great, I've learned something. I'm not going to tell his name, but even my greatest enemy, the chief of the opposite, banned theoretical physics, who is a Nobel Prize winner, sent a message to me saying, fantastic, the little book, I loved it. Yeah. Right? So this is but the student of physics who just studied that at school reads what I'm saying and get nervous because say, wait a minute, I mean, there's all missing here. I got an email say, you talk about quantum mechanics in the 7th lesson. You don't even mention the Schrödinger equation. I thought, yeah, that's right. I don't mention the Schrödinger equation, but that's not the core of the story, right? So yes, and this connects to your question, what you were saying before, because to do that, you need to understand something all the way through. So once we have totally digested something, then you can just bingo, in one phrase.
You can whittle it down to the essence.
To the essence, right? I mean, take Copernicus. If you read the book of Copernicus, it's 300 pages of calculations, detail, geometry, perspective. It's horrendously complicated. And the equant, and he has the epicycles still, and this and this and that. And to make this complicated, the moon is complicated. What is it? 400 years have gone from Copernicus. Now we have digested everything, right? I can say in 2 lines. The Earth is spinning and is moving around, is orbiting around the sun. That's what Copernicus has clarified. Right. Okay? So it's totally clear. It's strange if you think about. We're actually moving. It's revolutionary. It changes everything. The Earth is a planet like the others. But it can be said in 2 lines. Once we have really understood something, at the end we can say it in 2 lines in a way that has it really, and the people understand what it is. So my ambition, but we're not there, would to do the same I just did with Copernicus, the same with, the standard models, special relativity, general relativity, quantum mechanics, quantum field theory, quantum gravity.
Yeah. You said in one piece you wrote, sometimes dreams come true. I felt there was a story about the adventure of physics that had to be told, but I thought people were not interested. But you were wrong. You were dead wrong, because a lot of people were interested. Millions of people have read your book. It's translated into dozens of languages. What do you think you got wrong about estimating people's interest in this subject matter?
No, I don't know. It was not just me wrong. The 7th lesson of physics was printed in 5,000 copies.
Yeah.
At the beginning. So that was the estimate of the publisher that was going to sell.
Do you think it was because you whittled down to the essence and you left out the equations?
No, I think no. I think it's because mostly because of the last chapter of the 7th. I think that's what made the book. So it's a book that is not just about physics. It's a book that tries to go down to the essence and then ask the question, all right, so what does it mean for us? How does it reflect on the way we see ourselves, and the way we think about the material, the physical world, and our, let me use this strong word, spiritual world. And I think that, let me tell you my interpretation of that. It's I and my friends and many people around me share a view of the world which is not much known by the large majority of the population. And it's a view of the world that is neither, the world is made by little atoms bouncing with one another, and that's it. So, emotions, the sense of lies, whatever, that's bullshit that come later, is neither that, is not that, but is neither, the material world is irrelevant. There is a spiritual world with, God, morality, and thing. That's what reality is. Somehow, a lot of people are unhappy with both because they don't believe the spiritual world too much anymore, because we're in a secular society which doesn't hold anymore for a large number of people, and less and less and less. Mm-hmm. But neither people find convincing a sort of cold and ground scientism which has no hold for meaning, for emotion, for our aim, for what we are as thinking and desiring and suffering. So the fact that somehow people find in my book a perspective where the two things can very well stay together, and there's no contradiction between one another, is what a lot of people jumps in and say, oh, but then there are people who can, think that what matters for me is my emotions, but also there's nothing in contradiction with fundamental science there. I think that this is bringing together that make people react.
And regarding this goal that you have in your writing of getting to the essence of a concept, I would think this would be uniquely challenging when you're talking about something like time, because the average person will probably talk about time at least once in a typical day. So there must be a lot that you need to strip away, because the average person has a lot of assumptions that they're making about this word time. Can you tell us about what that process was like when you're describing time?
Yeah, I mean, absolutely. I wrote a book just uniquely, entirely about time, and that was not an easy to write book, because exactly for the reason you're asking, you're pointing to. And when I decide how to write this book, I exactly ask myself this question. And so the first half, the longest half of the book, is just one by one. One chapter after chapter, demolishing something we give granted for time, and on good grounds, on things we know. So we think that time has this property, and it seems obvious to that. That's the way we think. And now I tell you, it's not the case, and I'll show why we know it's not the case. So the first part of the book, it's just a way of telling Boltzmann theory, of telling Einstein's special relativity, putting the various pieces of the story together. But not just for talking about physics, for talking, look, what this imply with respect to our notion of time. Special relativity definitely changes our notion of time. Notion of present everywhere in the universe doesn't hold. But it's hard to think the world without a notion of present everywhere in the universe. The question, what is going on right now on Andromeda, the galaxy, is meaningless. There's no meaning in what is going on right now. There's no now in Andromeda. So they're asking, what is going on here in Beijing? I mean, no, we're not in Beijing, so there's no here in Beijing. Beijing is elsewhere. So to the book was designed exactly to address what you are saying, to take away one by one the presuppositions of people that people give for granted in science. And as some of my colleagues, which are very reflective, and they read a book, there's absolutely nothing they learn because they have gone through that. But there are a lot of my colleagues that teach special relativity and never have stopped and thinking what actually they're teaching. And I think that's wrong. I mean, physics is interesting because it tells us something about the world, not just because you write equations and then you make prediction and it matches with what you measure.
And are you yet at a stage where you can give this 1 or 2 sentence definition that's the core of what time is?
No, with time is very complicated, and the reason is exactly because we haven't got to the end of understanding it. There are things about time which I think we're generally confused. A lot of things we have figured out with total clarity, like the non-existence of a present everywhere in the universe. Um, but there are issues about how to think about time in a fully consistent way with everything we know, which I don't think we have figured out yet. Even the direction of time is complicated because we have connected it to entropy, to the macroscopic description, but there are definitely holes in our understanding, in my opinion.
I found that book, The Order of Time, to really make my brain meld and squish in other directions. And I found it ironic. I was listening to the audiobook, and at one point I was rushing somewhere, and something you wrote about time made me think, why am I rushing anywhere? A rush is an illusion. But I appreciated your writing of that book. I also really liked Benedict Cumberbatch reading it to me. That was a nice experience. Boy, it helps when these concepts are
he's
so mind-bending.
Good.
Yeah,
yes. I've been listening to his voice and saying, "Wow, who wrote this wonderful things? I mean, that's too good for certainly not me." He has a way of making it comprehensible, but also it's like it's talking to you and telling you like a friend. It's quite wonderful.
Yeah. Well, we actually have another student question about your books. Do you want to introduce that?
Yeah, we have this question was sent in by a PhD student here at Perimeter.
This is Matt Duchenne, a student at IQC and Perimeter. I'm wondering, how did you first get started into writing science books, and how has that writing helped your own research? Do you find writing a technical paper or a more accessible book more challenging?
So what's trickier, a detailed scientific paper or a popular piece of science writing for a general audience?
Probably a book for a general audience.
Why is that?
Because roughly you write a scientific paper after you figure something out. So you just get confused in a problem and either alone or with somebody else in physics. We work mostly in little groups of 2 or 3 in theoretical physics. You sort of come out and some point is clear, and then you write it down, and you write it down what you have understood. So the writing is relatively easy. I'm picky. I'm complicated in writing scientific articles. I try to write them clear, so I spend time writing, rewriting, perhaps more than what I should or could. But the writing is you know what you're saying exactly. While when you're writing a book, you still don't know what you're saying. You're making up what you're saying in the writing itself. So for me, it's complicated, and writing for me it's a complicated process. So it's not my books are the result of a large number of revision and the large number of cancellations. They take away a lot because they say, "No, this is not useful for what comes," and that's just superfluous. So I take away, and then the same phrase I rewrite it 10 times. I say, "No, that's not clear. I mean, is there a way to say it better?" That's a harder part of writing for me.
I was just going to say, for you, it seems that this must be particularly challenging because you're not just writing a book for the general public. As you said, you're hoping that your book will be influential for the general public and also for experts in the field, even though the material is not technical or maybe doesn't rely on math. So I would assume writing something that can be a good fit for both of those audiences must be very challenging.
Yes, it is. And I have these 2 readers in mind: the super expert one who knows everything, and the one who knows nothing, which is good because thinking that the super expert one is what warns me for not saying something. Which is, no, if I say that, he's going to complain. and thinking about the prototypical grandmother who doesn't know anything. Stops me from saying things. I mean, that's too complicated. I mean, how can anybody get this point? So I always have to struggle. So this simplifies because it gives me guidance. But yes, it's also a complication. Because I'm putting my own ideas in the books. mostly because it's my own perspective of things. I've written a book on quantum mechanics, Helgoland, which is entirely from perspective of Heisenberg, Born, Dirac, rather than from the perspective of Schrödinger. So it's taken quantum mechanics because I think it's the most interesting thing. I'm not the only one, but there are people who think different. Who think, no. Quantum mechanics is all about the wave equation, Schrödinger equation, the wave function evolving. That's all there is. I think that's wrong. So I give a different perspective. So it's my books are a way of defending a perspective. But the two things help one another because in the moment in which you try to explain something simple, you get clarity yourself. I mean, for me, it's not an exercise; it's an exercise of science. I feel I'm doing science when I'm doing that. I'm clarifying my mind. And reading at the great masters who are infinitely better than me. I mean, reading Galileo when he writes these books, it seems to me he's doing exactly the same thing. I mean, he's talking to people. That's a book written for the cultivated person of the European Renaissance in the 17th century, not for his colleagues astronomers, because it explains things one by one. But obviously, it's debating with his colleagues astronomers in the book. It's making the subtle points of the argumentation, proving him right and them wrong in that book. So he is doing both things. And that's what makes that book so great. Now, of course, I'm not Galileo and I'm not writing the dialogue of the two great systems. But it's this kind of popular science, which other people are doing, which is presenting ideas in a way which are comprehensible to defend these ideas, which I'm trying to do.
Are you working on any books now?
Sorry?
Are you working on a book now?
Yeah, I am, but I'm not sure I should talk about that.
Are you always working on one book or another?
No. I have not been writing for 1 year or more. I just stopped completely. I'm under strong pressure, of course, from publishers and things for writing more. And now I think there's something I want to do. Let me just give you this. I'm not covering a large portion of physics. I want to do the narration, tell the story of how a theoretical physicist like me get into a specific problem, get fascinated by the problem, work through and come out with some ideas and struggling on. So whether this particular thing is right or wrong is irrelevant. I want to tell how is theoretical science in the doing.
Is it sort of humanizing the process or putting
yes,
making it relatable to non-science?
Yes. To show what is actually going on, including changing mind and realizing things didn't work and so on and so forth.
Excellent. Well, I don't actually have any further questions. We've kept you for more than an hour, I believe.
Wonderful.
So thank you so much for chatting with us.
Thank you.
I'll just ask a question I always ask people when I interview them. What keeps you up at night these days? What problems or challenges are rolling around in your brain?
A very last night I was awake with my brain going around.
So it was a relevant question.
Yeah, absolutely. There is a beautiful experiment in quantum gravity, in fact, is being proposed, and there's some people who are questioning the way to think about that, and I think they're wrong. So I'm trying to find out a right theoretical description of this experiment. And in doing that, it's fun because it's basic physics, but it's writing things in a new ways, and there are technical issues, technical problems. So I keep going around these things here. So it's not a big, huge question. It's a very small, specific question.
Well, we'll have to have you back another time so you can tell us the results of that. So thank you again. This has been a pleasure.
Thank you very much.
Thank you.
That was very nice.